Hello everyone, welcome to this problem solving session. So we'll start with the today's session. So our this week content was mainly related to solar cell and photo detectors. So I will give a brief summary of solar cell and the photo detector, whatever the content presented in the, the this week lecture. And if you have any doubt for related to these concepts, and just raise your hand and start asking your doubt. And if you have any doubt from previous session, just let me know, and we will solve those doubts. And if you have no doubt, then we'll start just ahead with the session. I will pause for a minute, and then we will just start with the session. Okay, so let's just get started. The basic concept is the solar cell. Basically, those initially was like invented for like the space applications, especially on the satellite. Like that is a electronic device, and to power that, and for that you need actually sort of uh, like energy generator or something. So if you send anything for from the earth, that like the cost per unit mass, or like the mass it will take, you have limitation. Basically your like the those satellite launch vehicle, and those also has a limit actually. So you can't take infinite amount of fuel or those to like generate those electricity and those things. Also like the in the space actually there is enough amount of solar radiation available. So basically you can like you can generate the energy without any much if like much difficulty. And you can basically you can and that does not require like much of the mass to be burned by like by to generate the energy. So that was the idea behind. So initially the solar cell was like initially the solar cell was invented for space application. And because in space there is not cost constraint is not much, because like you don't need to produce for mass scale, suppose to put at your home, and like to put at much larger scale. Because like in a space like your satellite, or especially that international space station or those kind of application, you don't need much larger electricity compared to our household requirement. So that basically you can use like the cost is not in the all concern. You can use best material. So uh, we will see best materials like the for generating any kind of photoconducting or photovoltaic devices. Best are like direct band gap semiconductor like gallium arsenide or those kind of material. Because that has like the it generates, they have high uh, uh, like the high efficiency. And because of that like they are best suitable materials. But so the for solar cell actually the important is not just only to generate to generate the voltage out of the many photons which converts the light spectrum. But the problem like in the solar cell is basically like how much like uh, because the sun has a behave like a black body. So it has a peak spectrum near to some wavelength actually. So this is around 1 micron wavelength, which is the band gap of silicon. Around that is around 1.1 electron volt. And that basically if you are taking the silicon solar cell, that below this only you can generate the photon. Above this will not generate photon, because that your energy is less than So this is the wavelength, and this is the your your uh, 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 spectra of your like number of photons or power you are getting. So basically, your spectrum, solar spectrum, is like how this is how it is distributed. So you see, like all the wavelength does not have same same number of photons flux or like the power flux we don't get. And so because of the so ideal solar cell, basically what do you want? You want to capture this all spectrum. So to do that, basically you need to use this smaller and smaller band gap material. But the smaller band gap material also has a problem, because then it's basically your open circuit voltage and those efficiency will drop in those cells. So basically, so you want to capture this whole spectrum, but only the relevant part of this spectrum you can say is this much. So that's why even people stick with for mass kind of solar cell. People stick with the silicon technology, and especially people were like the you see around like the quite a number of amorphous silicon solar cell also is there, because that the cost wise it is better. So you can compromise some efficiency in terms of cost, and then you can have better better penetration of installation. So basically, so if you so ideally, a solar cell is nothing but a PN junction. So if you PN junction, and if you connect the PN junction by a resistor, so basically this PN junction, if you shine a light, or radiation, this will absorb light, and then it will generate electron hole pair, and then those will be, because of the field, it will be if those are generated within the PN junction PN junction region, then they will be drifted away by the electric field in the junction, and because of that that leads to generation in the current. So the total current of the uh, solar cell is given by this minus I times L plus Is times exponential of QV by KT minus 1. So this is basically the dark current, and this is the current due to light. And basically if you if you see this equation, so that you will find that the characteristics are similar to at zero light. So you will see the BJT like the PN junction has this characteristics, and if you generate that, if you shine more and more photons, then this light current component added. So basically, you will start having the characteristic like this. So so as you increase more and more light, so IL increases, and your solar cell will generate more and more current. So there are two important parameters. Are one of the two important parameters is when this. So this is I short circuit current, and this is open circuit voltage, and basically that determines your characteristics of your solar cell actually. So then basically this and you can determine the efficiency at like the if you are operating at the at this. So basically your efficiency is power out by power in. Power in basically comes from the radiation or photon flux, which is falling times the the photon generation efficiency. Power out is related to what is the maximum the voltage is getting generated times the current. So the maximum efficiency, as you can see, so in this kind of scenario, actually, the maximum efficiency only occur at a certain voltage when where like this is Vm and this is known as the power maximum. So this is power versus uh, voltage plot, and you can see like there is a uh, it's not like very like at this point also the power transfer is not adequate because the current is zero, and at this point because the voltage is zero, so that's why no power transfer is there. So like the best limit like in between this, so this is that so basically your efficiency lies like how much best rectangular you can fit within this IV characteristics, and that outer the one is that this is known as the maximum which is theoretically possible, or in very ideal case if your characteristics are very vertical or sharp, then you will get so the efficiency is basically uh, uh, defined as Vm and Im. So this is defined in Vm and Im divided by Pn, and this is known as the fill factor actually. So this is fill factor is known as the VMIM divided by VOC ISC. So how much large this area compared to your or like the area bound by your open circuit and short circuit voltage, that basically determines your fill factor, and you can write this efficiency in terms of fill factor. So that is given by VOC times ISC divided by power input times the fill factor. So that is your efficiency. So if you have larger fill factors, then you will get more and more, more and more uh, more and more efficiency, and but there is a limit of efficiency you can achieve with the solar cell, and that is known as the Shockley-Quasar limit, and that for a particular solar cell it limits the around 33% of the efficiency of the solar cell at around some like 1.3 or something band gap. So basically, like you, so ideally, the idea behind the solar cell is basically so you want to like use as large spectrum of the solar which is available, depending on like you want to use all the photons, but for a depending on how many like how much uh, which type of solar cell you are using, you will operate in some fraction of the total spectrum. And also there is like the some efficiency loss in the solar cell because of the various factors. For example, uh, like there is the absorption in the like absorption of the photon, absorption on the of the radiation or photons in the environment, or like in the atmosphere. So that atmospheric absorption of different sort of wavelength leads to the efficiency drop. Also, like the photons also does not reach directly to the junction, so we create some kind of window material to make this PN junction. So there are some absorption and some loss of photons in those like while actually reaching the photons, uh, reaching the PN junction, there is a significant number of losses are there, and some photons are just reflected due to air and those dielectric materials of the photovoltaic cell materials. And there are like different kind of systematic issues and those kind of issues, like for example daytime, like the sun is not uniform throughout the day whole day, so that also leads to a drop in efficiency because you don't get throughout uniform radiation throughout the day, or different seasons and different kind of environmental conditions, like lot of practical issues are there for solar cell. So there are like people actively working on this, and So with the solar cell, actually you generate a power, and like the next thing in the photovoltaic or photoconductive devices is the photo detector. So basically, people say like the a bad solar cell is basically a good photo detector. It's good photo detector. So basically, in photo detector, what you do you want? It should work on a particular wavelength or set of wavelength. So that solar cell can work, but that basically you make the photo detectors, and there are like some different types of photo detectors are there. So most basic are these PN junction photo detectors. So you make a PN junction, and then basically you inject a light, and that some part of this absorb, and at the junction it will generate a photon, and that photon it's converted to the electrons, and that basically lead to generation of current. And like that basically you can define as a photo detector. And like instead uh, uh, with respect to like this biased so this solar cell actually we does not provide any battery, but we can operate detectors in different kind of mode. We can use with the zero bias, or we can use the photovoltaic mode, or other type of mode which are possible. So those the photo detectors. Mainly the photo detector, basically you want to generate the photons at a particular wavelength, actually uh, with a particular kind of material. And there are different kind of materials. Different kinds of materials are there. Some direct band gap semiconductors and indirect band. So indirect direct band, because they have the radiative absorption and better radiative absorption and emission characteristic. They are better suited material uh, for uh, for different kind of material systems. And also there are different kind uh, 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 other kind of materials, or other kinds of photo detectors are also there for like the normal typical PN junction type of photo detectors, and then they are PIN type of photo detectors, and then they are like avalanche type of photo detector. So basically, these are like these are very sensitive. Actually, you can like the you can implement the photon counter based on this avalanche photo detectors, and the other PIN types of devices. And actually, you can use as a because that offers some better advantage compared to the normal PN junction photo detector. So those are one of the important devices in the uh, in the in the whole spectrum of photo detector. So that was the brief outlook of the. So let me talk about the photo detector uh, 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 metrics. So basically, one is the quantum efficiency. So quantum efficiency. Other is the responsivity. So the quantum efficiency is basically like how many number of number of electron hole pair generated per unit photon flux or per unit input of the power. So basically, you just define this quantum efficiency. Also, that the responsibility is defined as there's the as the as the how much current per unit input of power, how much you generate. That is known as the. So the unit is this ampere per watt. So how many like what input power you get, how much current, that is just known as your responsibility, and that these are the two one of the two important parameters for devices. So that you can use for to characterize this photo detectors. So with this, let's just move mm, to the problem solving session. So I will wait for some time. If you have any doubt, then you can ask me, or I will pause for some time. Okay, so let's just get started. So first problems uh, talks about this. Consider a slab of silicon 5 micron thick. Determine the percentage of the photon energy that will pass through the slab if photon wavelength is 800 nanometer. Take the absorption coefficient of the semiconductor at 800 nanometer. So basically, so uh, uh, so determine the percentage of photon energy that's passed through the slab if photon wavelength is 800 nanometers. So basically, so that basically, so this we are given. This, let's say this is slab of silicon, and this we are given as that this is 5 micrometer thick long, and we are injecting photon from this side. So we are putting photons from this side. So basically, so some photon will get absorbed, and like throughout the material, some photon will get absorbed, and that like the remaining photon will eject out of this at the other end, and that will govern by this total intensity is given by the I naught times exponential of minus alpha times z. So that z is basically given as a 5 micron, and the absorption coefficient is given as alpha is given as 1000 per centimeter inverse, and z is given as 5 micron. uh, so that is 5 into 10 power minus 4 centimeter, and that so the uh, the total number of photons which get absorbed in this. So basically, so uh, so basically, the total number of photon so total number photon will like at the intensity at the end of this will be this. So this is the intensity at the end of this slab. So basically, these many number of photons are ejected out, and you can basically calculate the efficiency just by calculating this I by I naught ratio times the 100. You will get the efficiency. So that is equals to exponential minus alpha times z, and exponential of minus alpha is given 1000 times 5 into 10 power minus 4 centimeter. So this will become exponential of minus zero point 0.5. This will become exponential of minus 1 by 2, or this will become around 60% actually. 60.6% is the efficiency. So if we choose among the options, so the correct option will be this one, a second option. So this so the this is a straightforward formula substitution kind of question. So next problem, let's just move to next problem. So consider a gallium arsenide of thickness 10 micron at 300 Kelvin. If photon intensity of this zero point 0.4 watt per centimeter square, lambda equals to 793 incident on if the absorption coefficient is this 10 power 4 per centimeter cube, and the excess minority carrier lifetime is zero point 0.1 microsecond. Then the steady state carrier concentration due to the incident photon uh, intensity is basically how much is your uh, so this uh, uh, excess uh, excess concentration due to incident photon energy is given by this. So so basically like if you integrate, so the excess the generation rate is basically delta excess carrier generated divided by lifetime. This is basically equals to the alpha times h of f, and basically that basically delta n, from here you can calculate alpha I times h of f times the tau, the lifetime. So basically you can calculate, you can put this so you can put all the values. This is 10 power 5, and this is 0.05, and this is 1.563 times 1.6 into 10 power minus 19 times zero point 0.1 into 10 power minus 6 microsecond, and which if you solve by the equation, then you will see around 1.9 into 10 power 14 per centimeter cube. So the correct answer, which is matching near to this, is 2 into 10 power 14 per centimeter cube. So to get so basically so this is the so like to drive this formula basically, so you need, you know that uh, the intensity at a particular location is given as I naught times exponential of minus alpha z, and if you integrate this intensity equation into this throughout the length, and if you multiply by the area, then you will get the total number of photons which is absorbed by this piece of semiconductor, and from that you can calculate how many number of uh, carriers generated just by multiplying with the lifetime, and that basically gives you this equation actually. So the direct formula, this comes from the integrating this absorption characteristics within the semiconductor. So that was this questions. So let's move to next problem. So next problem talks about is a solar cell is example of which kind of devices. The first option talks about the photoconductive devices. So basically, photoconductive devices are the devices in which the resistance is on based on the number of photons you uh, implement inject. So they are kind of different kind of devices are there for like the like you can generate the so suppose if you take the piece of semiconductors, so if you generate more and more carrier inside the semiconductor, then basically you change the conductivity of this semiconductors, and this also you can use as a kind of photo uh, photo kind of to sense the photons and photoconductive devices. So basically to make this light dependent resistance and those kind of devices, LDR, light dependent resistance, you make the semiconductor like this, and you calculate the voltage across this, and when you put the light, so the resistance of this photoconductive devices changes, and corresponding that leads to change in the voltage, and that you can use also as a very uh, kind of to have the and other type of this is photovoltaic. So basically you generate a voltage depending on the number of photon in incident. So basically in this you can't generate like without this kind of devices you can't operate in zero bias condition, because it does not generate any energy. But the photovoltaic devices are, or they can behave like a like a power source, and that can be used to drive the power, or to get the power that can be used. So the solar cell is one of the example of this photovoltaic cell. And other options are photothermoelectric. So basically, it says that uh, joule heating kind of devices. Basically, you so when the your device temperature, depending on your device temperature coefficient, your based on the heat generated, you generate basically the voltage proportional to the heat, and those kind of devices also you can use. And this is the other option is the phototransistors. So solar cell is basically a p-n junction devices, not transistors. So this is also uh, wrong, and that other is the volumetric devices, and that is also not correct. Okay, so the correct option is the photovoltaic, and that is the B is the correct option. So that so so yeah, so that next you can so next let's move to next problem. So a bar of silicon with a dot with 10 power 15 uh, per centimeter cube is exposed to sunlight such that the electron flow hole pair is generated throughout the bar. So this has a 10 power 15 per centimeter cube, and this is throughout the semiconductors. You are injected the photons at 25 10 power 20 per centimeter cube per second. You are generating uh, the recombination lifetime is 10 microsecond. Tau is 10 microsecond. The whole carrier concentration is perceived. And the so basically your total carrier concentration is basically your your total carrier concentration P is basically your P naught at equilibrium carrier concentration plus delta P. So this is the excess carrier concentration. And basically you can determine this by the generation rate is given by delta P by tau naught if your generation is uniform. So delta P you will get G times tau, and that G is given as 10 power 20 times lifetime is given as 10 into 10 into or 10 power minus 6, and that basically you will give around 10 power 15 per centimeter cube delta P. And that basically so the total P concentration will be 10 power 15, which is P naught, plus delta P, which is 10 power 15. So the total concentration you will get 2 into 10 power 15 per centimeter cube. So the correct answer is first one. So that is your so this was quite simple problem. So that with that, let's move to next problem. Consider a long silicon PN junction solar cell with area of this. So area is given as 4 centimeter square. At 300 Kelvin, it's operating at means at room temperature. The solar cell has an optical absorption coefficient alpha is given as 10 power 3 per centimeter cube, and the reverse saturation current IS is given as 7 picoampere, and the photocurrent IL is given as 1 ampere. Calculate the maximum power if the fill factor is 0.75. So this basically for this actually so we can calculate the open circuit voltage, and then we can calculate the short circuit current, and this the photocurrent this is IL is given with the light. And basically you can calculate if we calculate the open circuit voltage, then we can get the VOC times ISC. So the open circuit voltage is given as this: VOC is equals to kT by Q ln 1 plus IL by IS. So IL is given this. So this is 0.026 ln 1 plus IL is given as 1 ampere, and that is given as 7 picoampere. So if you put this value, and that basically you will find that the correct value of this is 0.667 around voltage VOC, and the fill factor is basically fill factor is basically VMIM divided by VOCISC. Uh, then basically so this is Vm by Im. This is your power. So whatever the output power you are getting in your circuit, so that is basically the power out is given as the fill factor times VOC times ISC. So that basically fill factor we are provided with 0.75 and the 0.75 times ISC is 1 micro 1 ampere, and this is around VOC is 0.667 volt, and that you will get around zero point 0.5 watt P out. So this is the correct answer to this problem, and this is the correct option is C and third option. So that is the correct option. Uh, now let's move to next problem. So basically, uh, so uh, this so this they a photodiode has a responsivity is uh, 0.25 ampere per watt, and basically uh, this basically it's generate like the it generates so you can calculate it is generating for per unit efficiency is so basically you can calculate the efficiency just by so uh, this is basically so this so the current is basically this responsibility gives the 0.25 ampere per watt, and this ampere you can just current you can calculate the how many number of electrons it's generated. So if you divide by 1 by E, then you will get so if you divide R by E, then you will get around the number of electrons it is generated electrons per unit input power, and basically from this electron you can calculate, and efficiency is basically your power power uh, so number so efficiency is basically a number of photons generated divided by number of photons injected. So if you put this into the equation, then you will see the responsivity is related to the the E times efficiency times the energy of photons. So that basically efficiency you can calculate the responsivity time energy of photons time divide by the electrons electronic charge. So basically so here like if you divide by the electronic charge, you will get the number of photons, and uh, then if you multiply with the by the photon energy, then you will get around the how much power it the each photon is generated divided by the input power, so that gives you the efficiency. So that responsivity is given as 0.25 times the this is given as the 532 nanometers. The energy of the photon is around 2.3 or 2.33, so you can calculate by 1.24 divided by 532 or 0.523 micrometers, and that you will reach at around 2.33 electron volt. And that basically if you can plug into this, you will get around 0.582 or 58% efficiency. So that is the efficiency or your photo detectors. So basically, the correct option is the second one. So this with that, let's move to next problem. A silicon photocell has a dimension of 4 cross 4 at this is the given as a 4 centimeter cross 4 centimeter, and the its eta is given as 100%, and initially the cell is kept in the dark. When the current of when a current of IL is this much force through the inlet in the direction of good conductor, the voltage generated is this VOC. The reverse saturation current we need to find. So basically, like the IL is given, we need to find IS in the in the solar cell, and VOC is given. So basically, you can get the VOC equation as KT by Q, ln 1 plus IL by IS, and that basically you can cal IL by IS is will become just like your exponential of uh, VOC by KT by Q uh, minus 1. Basically, this will become like this, and that you can no, this is in this direction. So that no, no, this. So basically, this will become exponential of VOC divided by KT by Q minus 1 times this is the current, and that in the forward bias or VOC equals to positive, you can approximate this as the exponential of VOC by KT by Q, and that IS you will get a key uh, IS you will get if you take this to bottom, so this will become IL times exponential of minus VOC divided by KT by Q. So that if you put the values, that is 100 microampere times exponential of minus 0.466 divided by 0.026, and if you reach this, and you will find this 1.5 1 point around 65 or 1.65 65 picoampere of current you will get. So the correct answer will be last one. So this with this, let's move to next problem. Consider the following statement: the PIN photodiode can be used a better photodetector than the PN photodiode. The intrinsic region width in a PIN photodiode is much larger than the space charge width of the uh, PIN photodiode is much larger than the space charge width of the normal PN photodiode. Uh, the intrinsic region width of the PIN photodiode is much larger than the space charge. If the reverse bias is applied to PN space charge, reproduce through the intrinsic region, and though there is no electron hole recombination. So this so so this basically in the PIN photodiode, basically you what you do is you uh, within the between the two P and N region, between the two P and N region. So you put a layer of intrinsic material actually. So because intrinsic material does not contain any like doped kind of uh, so or any kind of doping or fixed space charge ions are not there. So that means like if even if like this region is already having been depleted, and this is like this can be used, whole region can be utilized as a as a like the as a active region in which the field exists, and that you can use for like the photon absorbed within throughout this region will be absorbed, will generate the carrier, because there is a field exists to separate out those electron hole pairs, and which is much larger compared to normal PN junction diode which you see. And on that, like normal PN junction, that is a function of reverse bias voltage you are applying. But in this kind of PIN diode, basically that is independent of reverse bias voltage. And so the PIN photodiode can be used as a better photodetector than PN photodiode. And intrinsic region with the PN triode is much larger than the space charge region. So this is the correct option. Correct. And if a reverse bias voltage to apply to PIN diode, the space charge region extend completely through the intrinsic region and has no electron pair hole pair recombination. So basically, there is so in this region basically the electric field exists throughout the region. So that's why that this space charge this can be considered similar to the space charge region, but has you can control this width of this region actually. So that basically it's a better compared to the PN region where like the where the your width of the depletion region is directly proportional to square root of your applied reverse bias voltage. So that basically to get higher and higher uh, the depletion bit, and you need to put the more and more reverse bias voltage. But in the region of operation, you may have uh, a limit of the applied reverse bias, and also like you can apply the reverse bias up to only till a certain point, so that the device or junction breakdown does not happen. So that much only large reverse bias voltage you can apply, and that has a limit. So that based on this, the both the options are correct, and actually, so you can use PIN diode better compared to the PN junction diode. So with this, let's move to next problem. A uh, The figure shows the IV characteristics of the solar cell illuminated by uniformly with the solar light of power 100 milliwatt per centimeter square. The uh, the figure below shows the IV characteristics of the solar cell illuminated uniformly with the solar light of 100 milliwatt per centimeter square. Solar cell has an area of 3 centimeter square. Area of 3 centimeter square and fill factor is given as a zero point 0.7. The maximum efficiency in the percentage of the device is given. Uh, so, uh, the efficiency basically is given, N is given as the output power. So output power divided by input power multiplied by 100. So this is P out divided by P in times 100. So P out basically you can write VM into IM times P in times 100, and that you can write as a VM IM you can convert as the fill factor times VOC times ISC divided by P in times 100, and that basically you are given as the area is given like this 3 centimeter area is given, and per unit area the intensity is given. So the power input is given as uh, the intensity times area. So this is given as 100 milliwatt per centimeter square multiplied by 3 centimeter square. So this you will get 300 milliwatt, and that you can write as a zero point 0.3 watt, and that basically you can convert. And that basically an ISC and VOC is given from here. So that basically you are given as the fill factor as a zero point 0.7 times ISC is 180 milliampere, which you can write as a 0.18 ampere, times the VOC is zero point 0.5 volt. divided by your input power, which is 300 milliwatt, times the 100, and which like if you put in the number, then this will become 100, and like this you can write the point 0.3. So this you can uh, calculate this as zero point 0.1 times zero 0.06, and that basically you can remove this number, and basically this you can remove. So this will become zero point 0.7 into 0.06 times zero point 0.5 times 10. So this is will become 0.7 times zero point 0.6 times zero point 0.5, and that this will become uh, 0.03 0 point this will become zero point 0.3 times zero point 0.7, and this will become 0.21, and this like the efficiency, if you convert to the efficiency, so this will become around 21%. So if you convert into the percent, that will become your 21% efficiency. So the correct answer is basically is the C option. So that was quite simple. So with that, let's move to next problem. A PN junction solar cell of 1 centimeter area is uniform illuminated the following the parameter. This efficiency, N efficiency is 15%, and the open circuit voltage VOC is given zero point 0.7 volt, and fill factor as zero point 0.8, times the thickness is given as 200 micron. The average optical generation rate is given as we need to calculate the average uh, optical generation rate. So basically, so uh, so basically, you can like so if you can divide by the this area is given, and the thickness is given, so you can calculate the volume. So basically, you can calculate basically your short circuit current. So the efficiency is given. So efficiency is basically your fill factor times VOC times ISC, and ISC, and that divided by power input, and that basically from the efficiency you can calculate the ISC current. So that is efficiency time power input divided by fill factor times VOC. So this many number of electron will get generated within the that basically if you put the efficiency is 0.15% times the power input is zero point 0.1. So the input power is given uh, as 100 milliwatt per centimeter square. So so if you get like this, so this is given as 100 milliwatt per centimeter square times the point 1 centimeter square, you will get around zero point 0.1 watt. This is the input power, and then basically you can write the fill factor. Fill factor is given as zero point 0.8 times the open circuit voltage, and which is given as zero point 0.7. So that basically the current you will get from here is 0.026 ampere of current, and basically you can you can with this, if you divide ISC by Q, so you will get so these are the current is basically the coulomb per second. So if you divide by the coulombic charge, electronic charge, then you will get number of electrons per centimeter cube, electron per second, And if you divide by the volume, then you will get the carrier concentration by so these many number of electrons are generated throughout whole volume actually. So that basically you can get the if you divide by the volume, then basically you will get the how many number of electrons are generated within the cell of the volume of the cell. And basically so you can write the ISC by Q divide by the volume will give you the total number of total generation rate. Then that is given as 0.026 divide by 1.6 into 10 power minus 19 divide by 1 into 10 power. So this volume you can calculate area multiply by thickness, so which is given as 0.02 centimeters, and area is given as 1 centimeter square. So that basically it will reduce to 0.026 divided by 1.6 into 10 power minus 19 times 1 centimeter times 0.02 centimeter square. And because the units are same, so this will become 8.37 into 10 power uh, 18 per centimeter cube per second. So that is the correct. So this the power here is given as 8 times the 10 power 18, and this is the correct option is third one actually. So this was the last problem from my side. So if you have any doubt, I will pause for some time. You can ask any doubt till now I have covered, or whatever covered in the lecture session. Hi Sanjeev, you have any doubt related to the session today or previous session? Sorry, yeah, yeah. Uh, uh. What is the answer for last problem? So it is 8 point, it will come 8.4 into 10 power 18 per centimeter cube per second. So this is because this was one of the gate problem. So 10 power 18 was already given. You need to find this uh, like the multiplication factors in terms of powers of 10 actually. So this the final this figure is this 8.37 you can approximate to 8.4 depending on the option into 10 power 18 per centimeter cube per second. So is that answer your question? Did I get your question correctly? Okay. So you have any other doubt related to solar cell, photodetectors, or any other device, PIM pin, or any other previous session doubts? Because I think this is mostly the second last this session actually. I think before exam. Before exam, there more also one more extra session I will take around 26, but this may be the second last session before next session. Uh-huh. Okay, you joined late. Okay. So basically, I just briefly summarize the solar cell efficiency of solar cell, photo detectors, and those kind of diodes and those things. and I solve some problem related to those. So, yeah. So, did you go through any lecture materials, or you have doubts related to those? You can ask, or you can go through this the problem solving. I will upload the video of this uh, as soon as possible. Then you can take a look, and then you can ask in the next class maybe. So, if you want, like, if you want, in, yeah. Okay. 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 Okay, fine. Okay, yeah, sure. So, so let's just so uh, so if you want me to get some like re-review of the problem which I solved, so then I think you just take a look, and then if you have any doubt, then you just let me know in the next class. Or so okay. So any other doubt from your end? Okay, fine. Okay, so thank you so much for listening. So keep learning and have a nice week. So so thank you so much for listening patiently listening this session, and we will meet same time in the same slot next week. Bye. Have a great night. Yeah.